the science of speed and endurance. You know the story. A hare brags about how fast he is. A tortoise challenges him to a race. The hare zooms ahead, gets so confident he takes a nap, and while he's snoozing, the tortoise just keeps going. Slow, steady, no stopping, and the tortoise wins. For thousands of years, people have told this story to teach one lesson. Slow and steady wins the race. Today, we're not here to repeat that lesson. We're here to ask a much more interesting question. What was actually happening physically inside that hare's body and inside that tortoise's body that made this outcome possible? Because here's the secret. This isn't just a nice moral. It's physics. It's biology. It's the actual science of how energy moves through a moving body. So let's take the fable apart, piece by piece, and rebuild it as a science lesson. The 3 things that describe motion. Before we talk about hares and tortoises, we need 3 words because you're going to hear them a lot. Speed, velocity, and acceleration. Speed is simple. It's how much distance you cover in a certain amount of time. If you run 10 meters in 2 seconds, your speed is 5 meters per second. Velocity is speed with a direction. Running 5 meters per second toward the finish line is different from running 5 meters per second back toward the start. And acceleration is how quickly your speed changes. When the hare exploded off the starting line, that burst, going from standing still to full sprint in under a second, that's acceleration. High acceleration takes a huge amount of energy, released all at once. The hare is a creature built for acceleration. The tortoise is a creature built for something else entirely, efficiency over time. Let's find out what that means inside their muscles. Let's talk about the hare's secret. Fast twitch muscle. Your muscles and every animal's muscles are made of 2 different kinds of fibers, and they work almost like 2 different engines built into the same car. Fast twitch fibers are built for power. They contract hard and fast, but they burn through fuel almost immediately, and they build up a waste product called lactic acid. That's the burning feeling you get in your legs during a hard sprint. Fast twitch fibers are amazing for a short burst, but they fatigue quickly. Within seconds to a couple of minutes, they're spent. The hare's whole body is optimized around this kind of muscle. That's why he can launch off the line so fast. But it's also why he needs that nap. His muscles aren't lazy. They're literally running out of quick access fuel and drowning in the chemical byproducts of going all out. Let's talk about the tortoise's secret, slow twitch muscle. Slow twitch fibers work completely differently. They contract with less force, but they use oxygen efficiently to burn fuel slowly, cleanly, and for a very long time without that burning fatigue. This is the tortoise's whole strategy, whether he even knows it or not. His body isn't capable of an explosive sprint, but it doesn't need to fight off exhaustion either. He just keeps converting fuel to motion, steadily, hour after hour. This is the real science hiding inside slow and steady. It's not about attitude. It's about which fuel system your body is running on. Now let's zoom out and look at champions of speed across the whole planet and notice something they all have in common. On land, the cheetah is the fastest land animal alive, capable of speeds over 100 kilometers per hour, about 60 miles per hour. But a cheetah can only hold that top speed for about 20 to 30 seconds before its body overheats and its muscles run out of stored energy. After a sprint, a cheetah needs to rest for up to half an hour just to cool down and recover. In the sky, the peregrine falcon is the fastest animal on Earth, period. When it dives after prey in a hunting stoop, it can exceed 320 kilometers per hour, nearly 200 miles per hour. But that speed only happens in a short, steep dive lasting a few seconds, powered by gravity as much as muscle. In the ocean, the sailfish and the black marlin are contenders for fastest swimmer, with burst speeds estimated around 100 kilometers per hour. And just like the cheetah, that speed is a short burst used for catching prey, not something they can sustain for a long swim. Notice the pattern? Every single record holder for raw speed can only hold that speed for seconds, not hours. That's not a coincidence. It's a law of energy. The faster you go, the more energy you burn per second, and no animal's body has an unlimited supply of quick-burning fuel. Let's take an example in human world, marathon runners versus sprinters. This exact same trade-off shows up in human athletes, and it's honestly one of the coolest examples of body specialization on the planet. A sprinter's body. Think of someone running the 100-meter dash, is built with a higher percentage of fast-twitch muscle fibers, bigger and more explosive leg muscles, and a training routine focused on raw power output over just a few seconds. A marathon runner's body is almost the opposite. More slow-twitch fibers, a bigger and stronger heart for pumping oxygen-rich blood over hours, and a body that's learned to burn fat as fuel. Because fat contains far more stored energy per gram than sugar, it just releases that energy more slowly. Here's the wild part. A sprinter and a marathon runner are essentially two different kinds of athletic machines built from the same basic human body plan. You could take two people the same age, same height, and depending on which muscle fibers they were born with and how they train, one becomes built for the hare's strategy and one becomes built for the tortoise's. Let's put a real number on this. The fastest human being ever recorded is Usain Bolt, who ran 100 meters in 9.58 seconds, reaching a top speed of about 44.7 kilometers per hour, 27.8 miles per hour at his peak stride. But Bolt's race lasted under 10 seconds. Compare that to the marathon world record, a distance of 42.195 kilometers, or about 26.2 miles, currently run in under 2 hours and 1 minute. That's an average speed of roughly 21 kilometers per hour, sustained for over 2 straight hours. Bolt is more than twice as fast as the marathon champion at top speed. But if you tried to make Bolt hold his top sprinting pace for 2 hours, his body would fail long before the finish line. He'd run out of quick fuel, his muscles would cramp under the lactic acid buildup, and his body would overheat. Meanwhile, the marathoner's body is precisely tuned to never ask for that kind of burst, so it never runs into that wall. So here's the real science underneath everything we've talked about. Your body has different ways of turning fuel into motion, and which one it uses depends on how fast you need that energy. When you move slowly and steadily, your body mostly uses aerobic metabolism, burning fuel with oxygen, cleanly and efficiently, which can continue for hours as long as you have fuel and oxygen supply. When you move in an explosive burst, your body switches to anaerobic metabolism, burning fuel without enough oxygen delivery to keep up, which produces energy fast, but also produces that lactic acid buildup, and can only last a short time before your body has to slow down and recover. Every fast-moving animal we've talked about today, the cheetah, the peregrine falcon, the sailfish, the sprinter, is running on that anaerobic burst system. Every endurance animal or athlete, the tortoise, the marathoner, is running on the aerobic slow burn system. So let's go back to where we started. The old moral of the story is, slow and steady wins the race, and that's still true. But now you know why it's true, at the level of actual biology and physics. Neither one was better. They were just running two completely different energy systems. And the real lesson hiding inside this old story is one that applies to cheetahs, falcons, sailfish, Olympic sprinters, marathon runners, and to you too, whenever you're deciding whether to go all out right now or pace yourself for the long run ahead. Understand your body, master your pace.